Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing, and for rest we are here to talk. So we were following our pattern wise DSS sheet and the topic was tree. Today we will do the question from BFS pattern. Basically anyhow we are doing the questions by both the patterns, means DFS also and BFS also, and this question also we'll do with DFS and BFS, but the best approach will be with BFS. So the problem name is cousins in a binary tree. Yes, and this is very relatable problem. So let's see the problem statement. It says we will be given the root of the binary tree with the unique values and the value of two different nodes of the tree x and y. Basically, we will be given the root of the binary tree and x value and y value. Our task is to check if x and y are in the tree are cousins or not. If they are cousins, return true. If they are not, means return false. Two nodes of a binary tree are cousins if they have the same depth but different parents. Okay, same depth but different parents. So if you will see example number 1, 4 and 3, they are present but their levels are not same. So if their levels are not same, the relation will be something like 1 is the grandparent, 2 and 3 are their children, and 4 is the grandchild. So for 4 and 3, they are the nephew or uncle or nephew, niece, or with aunt relation. So they are not cousins, right? So like this you have to check. 2 and 3, they are not cousin, even though their levels are same, but their parent are also same. Hence they are siblings. So for cousin, it is very important that their parent should not match, but their level should match. Let's see the constraint. Constraint says the minimum number of nodes will be 2. Okay, so for breadth first search, we don't need to write the base case. Works. Now the maximum number of nodes will be 100. Okay, this is the constraint is very small. So whatever approach we'll go with, either DFS and BFS, that is going to be fast only. They won't give us TLE because TLE occurs after 10 power 8 operations. How I know? Because we have discussed about the time and space complexity in our full YouTube video. I'll attach the link somewhere here. You can definitely check it out. So node value can also range from 1 to 100. Okay, and the definition has already been given. Correct? Also, it says each node has a unique value. Why it is important? Because if each node has unique value, it means we can stop iterating once we found the node value equal to x or y. Correct? Because if the node value was not same, we have to match with the nodes. But as it says values are unique, so we can stop once we found, okay, we have to find 4. We found 4, stop. Okay. So here is a node we have. Suppose you have to tell the relation between 4 and 3. Are they cousins? No, because they are not on the same levels, correct? Now, tell me the relation between 4 and 6. Are they cousins? They are on the same levels? Yes. Are their parents same? No. When I talk about parents, I don't mean the common parent. No, I mean just their parent. Means who's a parent for 4? 2. And who is a parent for 6? 3. Are their parents same? No. Means their parents are not same, but their levels are same. Means 4 and 6 are cousin. Okay. So how can we do this? Let's go with DFS approach first, and then we'll see the breadth first search approach as well. So if we are standing at root, okay. So what is my task? If root exists, what is my task? Can I say ki, hey root, is your value matches with x or y? Because x and y both are given as an integer. Let's say for 4 and 6 we have to find. Okay. So what I'll do, hey root, is your value matches with x? No. Hey root, is your value matches with y? No. Okay. If it does not, go towards your left and right child. Can I say that? So this is what required also. So what we thought, we are looking for ki if root exists, check with their values with x and y. If it matches, then what we need to update? Because at the end, can I say, it's like at the end, suppose we have the levels, okay? Suppose we have the levels and parent. So what are we supposed to return? Can I say, ki if x level, suppose level of x, equal to y level, correct? If level are same, and what? X parent not equal to y parent. Can I say, level same, parent not same, return true, correct? So return true, else return false. So I can say one thing, ki I have to fill these 4 variables. If I can fill these 4 variables, I can simply return true or false. But how will I fill these 4 variables? Means in the DFS call, where I was just sending my root, I have to send level also, because this will keep on varying from parent to children, correct? and the parent node also, correct? Why parent node is required? Because if I saw ki yes, x matches, like root value matches with x, then I need its parent to be stored, not root. So root's parent is very much required, correct? And what else? X and y, simply, if it is not known, correct? Now, what is the task? First, the base case, okay, if my root is null, return, correct? Now, next task, okay, if my root value matches with x, what I have to update? I can say ki, hey, suppose I will be standing at here, hey, my value matches with x. So what I need to update? Can I say ki x level will be nothing but the level of this, and x parent is nothing but the parent of this? Yes. So what I have to update? X level is equal to level, yes, and x parent variable is equal to parent. Very simple. Now what it will be, we'll see this later. Now if root dot value matches with y, then what are we supposed to do? Y level is equal to level. Similarly, y parent is equal to parent. That's it. Can I say? Very good. Now what we will do? Now what? Can I say I have to go, like initially I am at this node. I will say, is it null? No, it is not null. Is it matching with x? No. Is it matching with y? No. So now what is my task? Go towards your left side and go towards your right child, correct? So I'll call the function for left and right. So how we will call? We'll say DFS root dot left. Level will be parent plus 1, means level plus 1, correct? Parent will be, what will be the parent? Come on, think again. For root dot left, what will be the parent? Can I say the same root? Yes. So root will be the parent, x and y will be as it is, correct? Now for right side, root dot right, level will be level plus 1, very good. Now parent will be root only and x and y, that's it. Now let's do the dry run, how it will look like, let's see, okay? So we will have a stack something like this. First in the function we will have 1, level 0, parent nothing, so let's call it null, correct? Now what will happen? We'll go towards the left side, so function 2, level 1 and parent also 1, correct? Now we'll go for function 4, level 2 and parent 2. Now we found ki, hey, this node value matches with my x. So can I say my x level will be nothing but level, which is nothing but 2 here mentioned, correct? And parent will also be 2. So x parent will be 2. Can I return from there? No, I cannot. Why? Because I don't know what if my y exists towards, like downwards. I don't know. I cannot return. I have to look for it. Ki, where is my y? It's downward or it's towards right side. I don't know. So I'll keep on continuing. So again, I'll check, is it matches with like y? No. Then I'll go towards its left side, null. So it will get returned. Now I'll go towards right side. So in the stack, function 5 with level 3 and parent 4 will get saved. Again, we'll check, is it matching? No. Left side null, right side null, so it will get returned. Now when 5's left and right child will get returned, it will also get returned. So 5 call will get removed from the stack. So we'll remove our function. Now as 4's left returned, 5's also returned. So 4 also will get returned to 2. So what 4 will return? Simply as it is. So 4 call will also get removed from the stack. Now 4 was 2's left. Now 2's right, we have nothing. So this will also get returned to 1. So 2 call will also get removed from the stack. Now this was 1's left. So we'll go towards 1's right. What is at 1's right? 3. So this function will get saved. Function 3, level 1, parent 1. Similarly 3's left. Function 6, level 2, parent 3. We'll say, ki, hey 6, are you matching with x? No. Hey 6, are you matching with y? Yes. So y level and y parent will get updated. So what is the y level? Y level is nothing but 2. And what is the y parent? Y parent is 3. Correct? Yes. Correct. So can I return from here? I can return. So basically I have to again write the check. Ki if all my variables are filled, return. Correct? Anyhow, in the worst case, it does not make sense. Why? Because in the worst case, what if left child is towards the leftmost node and right child is towards the rightmost, like leaf node. Both are leaf node and towards the leftmost and rightmost. Then to anyhow you have to traverse through the entire nodes. Correct? So keep on moving towards it. After coming outside, once this DFS call is over, means these 4 variables are filled. If it is not filled, means either X or Y or both were not present. Okay. So now we'll check if the levels are same and the parents are not same, return true or else false. Very simple. Time complexity will be O of n because we are iterating to all the nodes. Space complexity will also be O of n. Correct. If it is balanced tree, then log n. Correct. But if it is not balanced tree, means skewed tree, so you will end up pushing all the nodes in the stack. Skewed tree means you have all the left, like any one side all the nodes present, or and other side very less number of nodes are there. So you will end up pushing all the nodes in the stack, and the space complexity will be O of n. So this was the DFS code. BFS code, space wise it is more optimized than this DFS. How it is so? We'll see it. So first let's write the code in the editor. So here is the DFS code for it. First we have to initialize our 4 variables. Then in the main function you have to call this, correct? And as a parent for the very first root is nothing, so we'll place null value. After coming all these variables, you have to check if the depth same and parent does not match, return true or else false. Now inside this we are just checking the base case check, if or else update the x value, x parent and y x depth, similarly y depth, and then keep on calling towards the left and right child. So this is your code in DFS. Let's try to run this and let's submit this. So this was your DFS code in Java. If you understood, here is your DFS code in C++ and here is a DFS code in Python. So the DFS code is more user friendly. If you are a beginner, you will definitely like this code will be definitely very much easy. Anyhow, the BFS code is also very similar, but the only thing is in BFS we will optimize the space a little bit more. That's it. Okay. So if you're done with the DFS, let's move on to the BFS. So what we are supposed to do in the BFS? First, we all know that root node will go in the BFS, which is Q. Then once we check if their value matches or not, then we'll go towards left side and right side. Correct? So we have to look for the false cases. False cases means in like definitely if they are cousins. If they are cousin, they must be present in the same level, means they will be present in that particular level and in the queue. Can I say that? So if they are present and their parents are also same, return false or else true then and there. Can I say that? Because you will have either this node, like means node present in the particular level, similarly 2 and 3, similarly 4 and 6. So if we were looking for 4 and 6, definitely in the queue we have 4 and 6, correct? So we can return the 4 and 6 then and there instead of checking 5 and 7. Can I say that? Yes, I can say. So hence 4 and 6 I will return true then and there. We don't have to look for later on. And the false condition is, suppose you have to look for 2 and 3. So what you will do, you will then and there you will check if your left and right values are not null, means they are present and they are matching with x and y, means they are sibling, return false then and there. Because that is our task, to check if they are sibling or if they are cousin. If they are cousin, return true. If they are sibling, return false. So if you found your left and right child are not null and matching with x and y, then why are you going to check in like the other nodes? Return false then and there. So in the BFS code, in the best and average case, you are actually saving your space. So in the BFS, what is the approach? Definitely if you have solved that level order traversal, if not, I'll attach the link. Level order traversal, you will keep on popping the nodes. You will check there, for sure this cannot be the nodes, right? So for sure you will go towards left and right child. If they exist, matching with x and y means they are children. Then only they are left and right child, right? To return false. Otherwise, store the children's right and left if they exist in the queue. Okay, and keep on continuing the same process. So this was to about what? For sibling we can return false. But what about cousin? So for cousin, I can say one thing now. I was running for one level at a time. So if both are present in that, then only I can say it is cousin, otherwise no, correct? So what I'll do, while I am running in the same level, I will pop and check if they are matching with x. Found x, make a flag, means flag of x, make it true. And if any value matches with y, make a flag y match and override with true. Why I did this? Because for cousin in DFS, two things were required, parent and level. Here level check we do not need to do. Why? Because BFS maintains it level wise. So if we have x and y at particular level, it means they are from same level. Why do we need to keep a flag for it? Correct? It is not required. Second thing is, Second thing was regarding their parent. So initially only I checked ki for parent, are their nodes matching with X and Y? If yes, they are sibling, return false. So if at a particular line, it has saved from this sibling part and they are present at the same level, it means we just have to check the flags now. If X found and if Y found. And if they are true, return true. If they are not true, means any one found. For sure, at that level, you found only one. So the other X or Y, whatever is rest over, is present in another level. So if it is present in another level, how can it be cousin? It cannot be. So return false then and there, isn't it? Yes. So first the base case, make the queue, insert the root until it is null, keep on running, calculate the size, make the flag for X and Y. Now this much for loop, you know na, ki this for loop we run for every level. So after coming outside the level, just think, after coming outside the level, we'll simply check if found X and found Y, both flags are true, means they are cousins. If any of these flags are true, any of these, it means one found at this level, another you can check on another level, it means they are not cousin. So return false, correct? Now in this for loop, what we are doing, we are popping the node, checking if their values matches, make the flag true, values matches with Y, make the flag Y true. This is the false condition, means sibling condition. If node ka root, nodes left, nodes right, means if nodes left child and right child both are not null, and if their values are matching with either XY or YX, vice versa, it means they are sibling and not cousin. So return false then and there, correct? And this code is to only insert the left and right child in the queue to keep on continue checking. And at the end, return false if you have not get the true. True means after every level you are checking ki, hey, these two nodes found or not. So if they were cousins, for sure at any of these levels, so they would have become true. Means both flags have become true at one point of time. If no, it means they are not there, return false. Very simple. Time complexity will be O of n, space will be O of n. But why I said in the best case it will be better? Because what if the tree are more longer, okay, and you were looking for 4 and 6. So 4 and 6 in third level only you got to know that they are present. So you have not went for the rest over checks, correct? So hence you will return true then and there. So that's where you are actually saving your space complexity and time as well, okay? Otherwise, both BFS and DFS approach are almost similar. So let's submit this code. So this was your BFS code. I hope you understood. If yes, so this was the code in Java. Here is the code in C++ with a similar approach if you are from C++ background. And here is the code in Python if you are from Python background. So if you understood this, definitely we can go in the sheet and mark the next question, which is cousins in a binary tree from BFS pattern as done. And do hit the like button if you understood, only if you understood. And subscribe the channel if not yet subscribed. If you have any doubt, let me know in the comment section. I'll definitely make sure to reply you all. And that's it. You will get the sheet link in the description below and you'll get my social media links also in the description. Let's meet in another video with some more interesting questions, topics and patterns. So then keep learning, take care of yourself and your family.